Hi, we are Project Altair from Islamic University of Technology, Bangladesh, and we are ready for ARC 2026 with our latest upgraded rover, presenting Musafir 3.0. Our journey began in 2023 with the merger of two former teams, Team Onirban and Team Ovijatri, with the vision of advancing space research and rover development in Bangladesh. Today, our team consists of more than 80 passionate students from various departments, and we work across 8 sub-teams: electrical, mechanical, software, science, management, creative, documentation, and public relations, all working together under a central team lead, collaboratively driving every aspect of Musafir's journey from design, engineering, testing, to fundraising, marketing, outreach, and overall project execution. Since the very beginning, we have been actively participating in international rover competitions. In 2023, our team ranked 10th in IRDC and secured 17th position globally in ERC, becoming second in Asia among 25 finalists. In 2024, our team received the Scientist of the Future Award at the International Rover Challenge. And in 2025, we qualified for the URC onsite on our first attempt and secured 18th position among 38 finalists, proving our dedication and mission to represent Bangladesh on the global stage. The astronaut is selected based on their comprehensive understanding of the entire rover system, including mechanical, electrical, and software domains. This enables them to diagnose and resolve issues across all subsystems effectively. They are also trained in stress management and critical decision making to operate efficiently in high pressure situations. In addition to system maintenance, the astronaut is responsible for controlling the rover and conducting on site laboratory tests as required. Our journey comes to life in our workspace, where every sub team connects and collaborates. In the lab, ideas develop into real systems as electrical, mechanical, and software teams work in sync. In our workshops, designs are fabricated into components with high precision and accuracy. Back in the lab, we test, refine, and solve challenges through constant iteration, planning, and smart execution. This is where Musafir is built, improved, and made ready for the challenge ahead. Our rover is equipped with sophisticated mechanical features including differential drive for seamless handling and a sturdy suspension designed to tackle challenging landscapes. The rover chassis was constructed using spare-edge stainless steel bars with a thickness of 2 millimeters, providing substantial strength to endure both longitudinal and vertical stress. For suspension, we used a part differential mechanism which ensures smooth mobility on uneven or rough surfaces. Our rover can comfortably climb inclined planes of up to 45 degrees. The rover weighs a total of 41 kilograms and is sized to fit within a 1.2 meter cubic volume. We've developed 4 custom wheels for our rocket suspension system. Each 10-inch tire has deep grooves for grip and an inflated tube for shock absorption. High-torque motors enclosed in stainless steel shells drive the wheels. Edgy 3D printed rims with bearings transfer the rover's weight, keeping the load off the motor shafts and reducing stress. Electrical subsystem is divided into 3 primary domains: power supply and distribution, control, and safety. For power, we use LiPo batteries as the main energy source for the rover. Power is efficiently regulated and distributed to all subsystems based on their requirements. A 24-volt rail is used to drive the brushed DC motors, providing the necessary torque and performance, while a 12-volt rail powers the arm actuators and other auxiliary components. The structured distribution ensures stable and efficient operation under varying loads. In the control domain, we implement an integrated architecture using ESP microcontrollers, Arduino Mega, and a Raspberry Pi. This combination allows us to handle low-level real-time control, sensor interfacing, and high-level processing simultaneously. To support this integration, we design and custom PCBs, improving system reliability, compactness, and signal integrity. The safety domain focuses on protecting the system during fault conditions. We utilize power MOSFETs-based switching circuits to isolate subsystems in the event of overcurrent or short circuits. This ensures that faults are contained quickly, preventing damage to critical components and maintaining overall system safely and reliably. An emergency stop switch is integrated into the system, allowing immediate manual shutdown. Our manipulator is a 5 degree of freedom robotic arm used for instrument implementation and maintenance tasks. The robotic arm is made from CNC-cut stainless steel plates connected by cylindrical stainless steel joints, providing flexibility and durability. It consists of 3 linear actuators for easy movement and navigation. The base rotation is implemented by a gear-based rotation system for improved precision and reliability. The linear gripper has been redesigned this year using a B-type mechanism, offering improved durability and strength. It can carry up to 5 kilograms of mass under full extension of the manipulator. The gripper enables the rover to pick up, carry, and place objects and is designed to handle complex tasks including opening drawers, putting in and taking out caches, open and close cabinets, operate flip switches, press push buttons, and control joysticks while also interfacing with electrical sockets. In a single workflow, it handles pipes, USB Type-A connections, and screwdrivers efficiently. It then performs sequential operations such as operating valves, adjusting mirror angles, cleaning surfaces with a brush, retrieving byte sensors, and typing keyboards. The entire science payload is fully integrated onto the rover. We begin with a high-resolution panoramic survey and a detailed geological scan. We use the deep sampling module, which can drill up to 20 centimeters into the soil. A motorized carriage aligns 3 detachable boxes with the DSM. Box 1 and 2 take raw soil samples from 2 different locations, mix and stir them with water. Box 3 stores the 10-gram subsurface soil sample as cache and seals it. 2 pumps transfer the soil mixtures to the science box to be dispensed into location-specific test tubes. Then chemical reagents are injected into the test tubes. Temperature and moisture sensors go 10 cm deep into the soil, and a microscope inspects the soil surface. Atmospheric sensors are also mounted on the rover and that streams live sensor readings. The storage cache is removed from the rover by the astronaut to measure the mass of the collected sample. 4 grams of soil is mixed with 20 ml of water, and the mixture is allowed to stand for 10 minutes to enable sedimentation. After settling, the supernatant is collected. From this, 2 ml of supernatant is taken and mixed with 2 ml of 5% sodium hydroxide, followed by the addition of 5 to 10 drops of 1% copper sulfate to perform burette test. A color change from blue to violet indicates the presence of proteins in the sample. We collected 1 ml of supernatant from ethanol soil solution, added 2 to 3 drops of potassium permanganate for base test. The light pink solution fades into light brown in the presence of unsaturated hydrocarbons. The ground station consists of ROS to enable control laptop running the autonomy stack along with RViz for real-time visualization of mapping, localization, and perception outputs. It is integrated with a radio master transmitter using Express LRS for manual control and a digital FPV receiver with a dedicated display for monitoring. The system is optimized for low latency, redundancy, and robustness. ELRS provides immediate manual override capability, while the Wi-Fi bridge supports high bandwidth data transfer required for ROS to processing. Multiple communication channels ensure fault tolerance in degraded or non-line of sight environments, such as lava tubes. The architecture supports GPS-denied autonomy, relying on visual odometry and onboard perception. In operation, the rover executes all tasks autonomously while the ground station monitors real-time data through RFS and FPV. Localization uses PixOx IMU and Radio Link SC100 GPS data with Intel T265 visual odometry serving as fallback redundancy. The rover autonomously navigates to prescribed GNSS coordinates. A custom-trained YOLO version 11 model performs real-time object recognition using RGB and depth data from the Intel RealSense D43-5i. The new obstacle avoidance module processes depth data to generate a collision-free trajectory to waypoints. Upon entering a search area, the local planner hands over the control to the Aruco subroutine. The rover performs a spiral search pattern executing 360-degree sweeps every 5 meters to ensure full coverage of the search area. For the peak detection task, the rover first performs a spiral search pattern within a 10-meter radius to ensure systematic coverage of the surrounding area. Using visual odometry and depth sensing, it evaluates the elevation data across the scan region, identifies the highest point, and navigates to that location. For basal detection, a trained visual model is deployed for rock classification. Due to the unavailability of limestone basal samples, the system is demonstrated using coal as a proxy material. The model successfully detects and classifies the target object, validating the perception pipeline, inference process, and integration with autonomous system. For the lava tube exploration, Aruco markers are used to detect entry and exit points. The rover tracks its trajectory using visual odometry and computes the tunnel length, which is transmitted to the base station. Throughout the mission, telemetry, mapping data, perception outputs, and live video are continuously transmitted. Manual override via ELRS is demonstrated to ensure operational safety and control flexibility. From soil to science, from data to discovery, our rover transforms exploration into insight. We are ready to take on the challenge. Thank you for watching.